This is a review of the Siglent SVA1015X network analyzer option. Siglent has many opportunities for improvement for this option. Anyway, I've always wanted a spectrum analyzer for my home lab. I've always preferred standalone instruments to PC-connected instruments because computers, OSs, and support software always eventually become obsolete. Standalone instruments, if well done, are usually much easier to use. The price, performance, size, weight of the latest generation of spectrum analyzers makes them a far more attractive option than used gear, since most used gear today is overpriced, of questionable origin, unknown functionality, and dubious reliability. The network analyzer seemed like an attractive option to me as well. I'd always wanted one of those. I use them at work all the time. I have integrated circuits I designed, measured with them, and I use them to measure other test structures and things I've designed, but I never get to play with them. The network analyzers at work are hooked up to dedicated wafer probers, and time is scheduled on them, sometimes weeks in advance, and they have dedicated operators. I never get to lay a hand on them. I can just walk in and look at them once in a while. Anyway, so far I've been very impressed with this spectrum analyzer, but disappointed with the network analyzer. The hardware seems good, but almost all of the issues could be fixed with firmware updates. I'm going to show you the issues I've had and suggest how I think they should be addressed and other improvements made. I certainly hope Siglent is listening, and with some firmware updates, they can turn this unit into a winner. Okay, the basic spectrum analyzer works for SVA1015X works from 9 kilohertz to 1.5 gigahertz, and has a tracking generator that works from 5 megahertz to 1.5 gigahertz. And for $13.95, this thing's pretty nice. It has bandwidth from 1 hertz to 1 megahertz in a 1-3-10 sequence. I mean, that's excellent performance for the money. The network analyzer option is an additional $609. It measures S11 and S22 from 10 megahertz to 1.5 gigahertz with a 5 megahertz minimum span. It's not really a full network analyzer. It doesn't do S22 or S12, so you can't get full 2-port parameters. However, in the future, I may go into how to do that. Anyway, if you're a ham, it covers the 30-meter band through the 23-centimeter band and could be quite useful. It always measures 751 linearly spaced frequency points, and the output power is fixed at 0 dBm. This unit also has some other options, a distance default option, which is not any good to me. I'd use a TDR setup. Advanced measurement kit adds a very nice waterfall display and a few other simple measurements. Hardly worth $419. Some modulation analysis, which might be good if you're using this in a production setting and measuring those, but certainly nothing I'm going to use. And then the EMI for $449 adds some additional bandwidths of 209 kilohertz and 120 kilohertz and a quasi-peak detector. I guess these bandwidths are standard bandwidths for doing EMI measurements, but to me, just poking around with probes and the standard bandwidths that come with the spectrum analyzer are good enough. You know, if Siglent were to package all these other options and price them at $400 or $500, they might be able to pry that money out of me, but the way they're priced now, they're not getting it. Anyway, the SVA1015X network analyzer has some good points and some bad points. The S21 works great for characterizing the gain and phase of passive devices, such as filters and attenuators. S21 can work with amplifiers, along with the judicious use of external attenuators, And S11 and S21 calibrations both work through attenuators. The measurement reference plane, now the bad points are that the measurement reference plane is behind the calibration plane and can't be moved for S11. This means you can never read the impedance at the point you want to read it at. I mean, that's the whole point of a Smith chart, is being able to characterize the impedance at a point. You can't do that at the moment. There's no adjustable delay parameter for the through for S21. This isn't quite as bad as this one, but it would be good to have, because oftentimes the length of your through is different than the length you're trying to measure, or you may want to offset it through some a piece of transmission line or something. It's good to be able to have an offset for this as well. Right now, there are no user calibration kits or editable calibration parameters. There's basically only 3 calibration kits for S11. One is a Siglent kit and 2 Keysight kits that are all based on male-in connectors. S11 does not work for many amplifiers the way it is, because 0 dBm is too high a level. It will drive most amplifiers into a nonlinear region, and when you try and use S11, let's say through a 20 dB attenuator, your return signal's down 40 dB because it has to travel both ways. They can maybe fix this, since the tracking generator is adjustable from 0 to 20 dB. From 0 to minus 20 dB for the spectrum analyzer. Depending on how their hardware designed, they may be able to fix this. Now, this system thing has a cumbersome file system and an ill-conceived user interface that truly suck. And we'll go into this. And it occasionally crashes and requires power cycling to reset. Hopefully these issues can all be fixed with firmware updates. Anyway, let's look at a couple of good examples. First, we'll look at a 240 megahertz high-pass filter, then a 755 megahertz low-pass filter. So here's the high-pass filter. Here's the magnitude of S21 in dB. You can see I have a dynamic range of almost 90 dB. That's incredibly good. And if we zoom in on this, you can see there's some ripples. Some of these may be ripples. Some of this just may be calibration. Most of these ripples, except these ones at the end, are well within the measurement level spec for this system. This is actually very nice. Here we're measuring the phase shift of the filter. And if we put a marker on it, we get at that point both the phase on this plus and minus 180 plot, as well as the total phase in degrees, or basically the total delay. These are both very nice things, and when you save the data file, you get both of these. And we can also get the group delay through this filter. This is excellent. Now, if we look at again, now here's the S11 on the Smith chart. We can see while it's in band, it circles around, but most of the stuff is staying right near the center of the Smith chart for a good match. And then once you get outside the pass band, it quickly goes to the outside of the Smith chart. So actually, if we started frequency, since it's a high pass filter, 10 megahertz is here. We come up here. This one is now at 240 megahertz, and these other 2 markers are shown up here. Here's the same filter. We're looking at the SWR at the input, and then zoomed in at the bottom. It's both excellent measurements. Nothing to complain about here. Now let's look at a 755 megahertz low-pass filter. So here we can see the magnitude of S21 in dB. And again, here now on the high end, maybe the dynamic range is a little less, or this just may, I don't know what's going on here. But we're already 70 dB down here. This is excellent measurements. Here, if we look at the same thing on a linear scale, we can see that You know, we have a few ripples up here. Some of they may be real, they may be measurement error, but they're tiny. This is again excellent performance. Here we're looking at the phase of the filter. So here's, you can see here as we go up in frequency, the phase keeps, in this case, decreasing. And so at each marker I have here, it's showing the phase. This first column is the crop phase, what it's showing on the plot, and the second column is the uncropped phase, assuming this just keeps going down and down. It's nice to have both of those, and if you save this phase in a data file, you do get both these values. Again, here's the group delay for this filter. Now, if we look at the input impedance of this filter, here again, here is marker 3 is at 10 megahertz. So it's a low-pass filter. So we're essentially right at the middle of the Smith chart at 10 megahertz. And we're staying inside until at marker 2 at 755 megahertz, we're just starting on this line, which is now outside the pass band, where it goes to the outside of the Smith chart. And so here we can see the standing wave ratio. Here inside, this looks like a lot of ripples, but this is basically, this is a standing wave ratio. Wait, no, this isn't standing wave. This is actually the linear magnitude of S11 here. So, you know, this stuff's real. And then up here, we're getting close to 1 because we're inside this is outside the pass band. Anyway, now let's look at measuring a high gain amplifier with this thing. Again, so this amplifier is spec'd from 100 kilohertz to 500 megahertz. It's got a nominal gain of 45 dB and a maximum output power of 17 dBm. So let's first look at a cal. So our calibration, when we do a through cal, since the output level of the network analyzer is 0 dBm and the maximum input level is 0 dBm, we want to make sure that the attenuation we have in line is greater than the gain, or we're going to overdrive the input to the network analyzer. So with 45 dB of nominal gain, I chose to use 50 dB of attenuation. And you can see here, you know, so I'm doing the through. This is actually measurements of the through cal after I've done it, and here I'm averaging the measurement, but the problem is that the cal isn't averaged. But you can see here that with 50 dB of attenuators in line, I'm getting less than 2 degrees of error over the range, and less than, what's this, 0.05 dB of gain error. I mean, that's through 50 dB of attenuation. That's actually pretty good performance. Anyway, yeah, so you know, you have to, so averaging isn't used for the calibration. It could, if you could turn on averaging for the calibration, I'm sure this would smooth out even more. And that's an option they need to add. Anyway, so here's a measurement of the amplifier. So the way I split up this 50 dB of gain is I put 40 dB of attenuation on the input. That ensures the amplifier stays out of compression. And I put 10 dB of attenuation on the output to protect the the network analyzer. Since the maximum output of this amplifier is 17 dBm, I put at least 10 dB on the output because I want to make sure that it never sees more than plus 10 dBm. Even though it says it's rated for plus 30, I paid a lot for this thing and I don't want to smoke it. So I'm going to make sure I never put in any more than plus 10. And hopefully for it to work, you want to put in 0 or less. So anyway, so here's the log magnitude of the S21 for this amplifier. You can see here the 3 dB point is 499 megahertz, pretty damn close to the 500 megahertz spec. And the phase is very gentle. It's actually a very well-behaved amplifier. Anyway, so now let's go into some of the bad points. Let's first talk about the S11 calibration and reference plane. There's no calibration kits. The calibration kits are not editable, and the reference plane is always behind the calibration plane. Anyway, so one of the reasons I bought this network analyzer is to measure components. You know, I sometimes buy bags of surplus components, and I'd like to know what they are, because sometimes, you know, I can't always tell from the marking. Sometimes you can, and you can't always believe what's in manufacturer's spec sheets, or the components you've picked up surplus may be out of spec. It's all nice to know, so it's good to measure them. Okay, and so one of the things I wanted to do was a reflection measurement on components. Now, you can get these Chinese SMAs now, if you buy them by the 100, for between 18 to 25 cents a piece. They're essentially disposable now at that price. I don't worry about using them. I can solder a component on, make a measurement, and then just, you know, toss it in my junk box if I really need to reuse it later. But I just grab a new one out of the bag if I was going to do it. Now, when you're measuring components, there's also a shunt and series through methods, and I may go into these more in a future video, but here I'm just talking about the reflection method of using S11 to measure the component. And so here, where I want the reference plane to be is right here at where the end of the SMA, so I'm measuring just the component here. Unfortunately, it doesn't matter which cal kit I use, it always puts the reference plane back here, or depending on the cal kit, a little forward back, but never where I want it. And since there is no port extension, I can't move it to where I want it to be. And so it's pretty hard to use a Smith chart if you're not measuring the impedance where you want to measure the impedance. I mean, this is a fundamental flaw in this unit. Now here's a short calibration I made. So here I cut off all the legs of the SMA and then soldered a copper plate down across it. So this is a solid copper plate with a hole drilled in it and then soldered across. And so here, and then I used that to calibrate the unit, and now I'm measuring this short after I've done the calibration. If you notice here, for the short, the calibration should just be a spot here on the left portion of the Smith chart, but it's not. It starts here at 10 megahertz and rotates around as the frequency changes. So now if I use the thing and plot the phase of that versus frequency, we can see it's pretty much a straight line. So it's basically just a time offset error. And for the short cal, I've got 19 degrees of error at 1.5 gigahertz. Now you can see here in the calibration menu, maybe they're thinking about doing this in the future. Right now, the cal kit cannot be modified, and the port extensions are grayed out and not enabled. Now here we're doing the same thing, but here I'm using an open. So here I've cut the legs off. I probably could cut that shorter, but that's not going to make a huge difference. But you can see here that this open should just be a single point here at the right portion of the Smith chart over the whole frequency. But again, it's rotating around as the frequency increases. And if we look at the phase, we're getting the same kind of phase change, but here getting 22.5 degrees of error at 1.5 gigahertz. I mean, if 2 or 3 degrees over that whole range I could tolerate, but this 22.5 degrees is just intolerable. And again, there's only the fixed cal kits, can't count, and the port extension's not available. This needs to get fixed. So let's look at measuring some components with this that I did. So here, I have here a 680 picofarad ceramic cap, 200 volt. I'm not sure who made it. It says high Q on it, but multiple manufacturers use this designation, so this is not unique. So if we look here at 10 megahertz, we're here, and it rotates around the Smith chart here, and then up here there's some sort of other funky resonance going on. So but if you look at if you start at the capacitive region here, as it rotates around, if there was no phase error, where it crossed this axis would be the resonant frequency of that capacitor. So when it's on this side, it's capacitive. When it's on this side, it's inductive. Right now, this is showing the resonant frequency at 97 megahertz. And basically at 100 megahertz and below, the error caused by that calibration plane offset is negligible. So this is an okay measurement. Now here I'm using looking at a Murata 0.1 microfarad ceramic capacitor. And it's crossing the axis at 11 megahertz. Again, that's well below 100 megahertz, so that whatever phase error is going on is minimal. But this 11 megahertz is better than the 8 megahertz spec in the spec sheet. So that's kind of nice to know, because I have a huge bag full of these things. Now here's a 3.9 picofarad ceramic capacitor in a glass case. And you can see here it's soldered on to the end of the SMA. So you can see over here at 10 megahertz, it's here. And as we go up in frequency, it's moving in at the Smith chart, as it should, as the magnitude of the impedance decreases as the frequency goes up. And it's crossing the axis here at 1.18 gigahertz. So if there was no phase error, that would be, say, my actual resonance for this capacitor is almost 1.2 gigahertz. But at 1 gigahertz, I've got essentially 16 degrees of error. So my actual resonance is probably close to 1 gigahertz here. So I've got an 18% error in the indicated frequency of resonance because I can't have the calibration plane where I want it. This needs to be fixed. Now here's another example. Here's an Allen Bradley resistor out of my collection of parts, and this is an Allen Bradley resistor. It's probably been in my resistor drawer for 30 plus years. So it's a 150 ohm, 10% resistor. This is the temperature coefficient. I don't remember what those, I'd have to look what the yellow band means. Anyway, these leads are very short. They should add a little bit of inductance, but for this thing, I shouldn't see any more than about 300 femtofarads or less capacitance, the way this is on here. Maybe a little bit more, but well less than a picofarad. And so here, so here at low frequency, it starts right on the real axis on the Smith chart, but as the frequency increases, it starts rotating around, and it's looking capacitive right away, and the capacitances it's showing are on the order of picofarads, and I'm not believing that. Because this rotation here is on the same order of the degrees of rotation I get from the calibration plane being out. So because the calibration plane is not in the right place, the measurement of this resistor is close to useless. Anyway, so what needs to be fixed for the calibration? One, they need to enable port extensions for S11 to make the Smith chart usable. They should also enable through extensions for S22. That will allow for the adjustment of length difference between the through cal and the device under test. They should enable at least 3 user-definable and nameable calibration kits, because most users are probably going to build their own calibration kits because, I may have build a component fixture and build my own cals for that. And there's many sophisticated users that may be able to do EM simulations on their own homemade cals, so you should add this. And then you should allow the saving and recall of cal kits in a text XML file and maybe use a .cal extension for it. This is not one of the options you have right now. Anyway, for cal kit parameters, for the load, you should allow me to enter the actual resistance, something I measure with an ohm meter, a time offset, and perhaps a parallel capacitance and series inductance. For the short, again, I should be able to enter a time offset and a series inductance. For the open, I should be able to enter a time offset and perhaps a parallel capacitance. And lastly, for the through, I should be able to enter a delay time, default about 60 picoseconds, which is a very short SMA through. But I should be able to change that. And I should actually also be able to add some programmable attenuation. The default should be 0 dB per gigahertz. So let's say I want to do it through calibration, but what I want to measure now, I'm going through a piece of cable whose losses I know. I can add those losses in and still get the measurements of what I want off somewhere else. So, this is all stuff that should be added into the calibration kit. Now let's talk about the file system. Right now, the CSV files contain only the parameter you plot, not all the data. So you have to go through multiple screens to save all the data, and it's really a pain in the butt. It comes up with default file names that are like CSV1 or PNG1 every time you do a save. And those are like meaningless file names. And to change them, you have to backspace, use a keypad, and the keypad's harder to use than an old flip phone was for texting. It's a pain in the butt. And there's no way to enter user comments. So I'm going to talk about these and ways these should be fixed. Decalibrate. Okay, let's look at the file system and some things that annoy me about this thing. So right now I'm in Smith chart mode, measuring a resistor. Again, as I said earlier in this presentation, this resistor should not look like that, but that's the calibration issue. So first off, if you go to the file system, you hit this file button, you can select either the local disk or the thumb drive. Save type, the default is actually PNG, which so if you hit save, it would just give you the option of saving a CSV file. Now there's always the option of doing a screen save by hitting this little spot down here, and this spot can be moved anywhere on the screen, but this corner seems to be a good spot, good place for it, because it doesn't interfere with a whole lot there. So you can see here's some files I've saved. Those file names mean nothing to me. So let's go back now to the measurement. And right now, let's go to Smith chart mode, and I'll put it in this. So you can see here, if I turn the marker on, it'll show frequency, real impedance, imaginary impedance, and what it thinks that imaginary impedance is in farads or henries. So if I go to save a file, a CSV file, it's only going to save these 4 columns. It's not going to save S11 or anything else. So here, if I look at log magnitude, look at the marker. It's only going to save the frequency and the log magnitude. Or here, if I save the phase, it's only going to save the frequency, and what one is the plus and minus 180 phase, which it displays, and one is the absolute phase, which will keep going through 180 to higher degrees. But it always displays the plus and minus 180, and it's kind of silly that it comes up here in plus and minus 300. It really should here. The default scale for this should be 36 degrees. So now it goes to plus and minus 180. Go back to measure, format, group delay. This will only save the group delay. So now if I hit save, it comes up and it says CSV. So since I've set the save type to CSV, it's going to say CSV1, and then if I save CSV1, so here we'll just hit enter. I go to save it again. It's now CSV2. Those are meaningless. And if I want to enter something each time, I have to backspace over it, and then use this funky little keyboard here, which is more irritating than the night texting on a 1980s flip phone. I mean, you can use plus minus and flip through the numbers. Okay, so I could do that. But then I go to do save, I have to re-enter that again. This is just very annoying and one of the key things that needs to be fixed. Okay, so let's talk about how to fix the file names first. Well, first off, we should be able to put user comments on the screen. There's no option to put a user comment. So Siglent always displays the time and date here. What they should do is move it over here and then enable the user to put a comment here. The default comment could be the model number of the network analyzer. But allow the user to do that. And then this little floating dot, one of the options on that dot should be able to change that user comment from any menu. Okay, so now when I go to save a file, the file name should be the user comment, then year, month, day, hour, minute, second in the file type, with all the spaces replaced by underbars. Okay, because now the file names will be meaningful because my comment will be the file name, and then it'll have the time and the date and time in the file. So if I save the files I save will be in order for the same comment with time and date. And and then when it comes up to save, instead of having just one default file type, it should ask me what I want to save. I should be able to save the data file, which is the CSV file, the image file, let's say a PNG, or the configuration file, which is the STA file. Okay, I mean, if having this now as the default file name would make life so much easier than dicking with that keypad every time to change the name. Now let's talk about the files themselves. Because right now you don't save all the data. You have to go through a whole bunch of different menus and save data multiple times to get all the data on the measurement. And it doesn't save some things I think it should save. So all the CSV files should have the following stuff in the header. It should have the model number of the unit, the software revision it's currently running, the mode it's in this case S11 or S21, the date and time, the user comment, the power on date and time, because I want to know how long it's been since I powered this unit on, because calibration, things drift with time, and I want to know if I made this measurement 3 minutes after I turned it on or after it's been sitting there half a day and stabilized. I'm sure they have some sort of internal temperature they can measure in the unit. And it's good to know this because I want to be able to compare this internal temperature from measurement to measurement and from with the calibration just so I can see that, if there's something screwy with measurements later, this is one of the things I could check. I want to know how many averages I've used for that measurement. If it's an S11, the port extension, or an S21, not S22 as I have here, but S21, I'd like to know what that extension time is. Default could be 0 picoseconds, but it should be there. The output power, right now it's always 0 dBm, but in the future I'd hope they could change this so they could go from -20 to 0. The measurement bandwidth, again, this is fixed at 10 kilohertz at the moment, but they may want to change this in the future, but that should be part of the what's in the header. The number of frequency points that are being used. Right now it's 751, but that they may change that in the future. So I want to know that, and they should have a default place for that in the header. I want to know the name of the calibration kit I'm using. I want to know the time and date of the last calibration. I want to know the internal temperature when it was cal'd, and how many averages were used for the calibration. And all of this data should be saved for every CSV save in the header. Now for the S11 file, we should have this is the columns that I think they should save. Not all these columns are useful for every measurement, but it'd be nice just to save these for every measurement. So if I make a measurement, I only have to save it once. I don't have to go through multiple screens to save the data. I can do this once. It would turn this from being a pain in the butt to use to something easy. I could quickly make measurements in the lab, and have it all there. Anyway, so the columns you should have for the S11 data are the frequency, the magnitude of S11 linear, the log magnitude, the phase of S11, the real part of S11, the imaginary part of S11, the standing wave ratio. Now, for the Smith chart, we'd want the resistance, the reactance, and then I'd also want the magnitude of the impedance and the phase angle of the impedance if I wanted to plot that, which as an analog guy, I often like better than the absolute resistance and reactance. Again, here, if we wanted to, for the Smith chart, the conductance and susceptance, but again, like before, I'd like the magnitude of admittance and the phase angle of the admittance. Now, instead of having the capacitance and inductance in a single column, you should have one column for capacitance, blank if you think it's an inductor, another column for inductance, blank if you think it's a capacitor. And then the last column should be marker labels. Instead of sticking something up in the header, you can just add whatever marker label you have for that row in the data, and then I can sort on that and quickly find the markers or subtract them from each other to get deltas. For the S22 data files, save less data, but a similar thing. You want frequency, the magnitude of S21 linear, the log magnitude of S21, the cropped 180 degree phase of S21 for plotting, the uncropped phase of S21, because that's good to know, the group delay, and then the last column should be the marker label as before. Anyway, so the 1050X VNA option, what needs to be fixed now? The first thing they need to fix is the port extension for S11 and the through extension for S22. Then the next thing would be to enable the user comments, both for on-screen saves and make it the default route for the saved file names. Then they should update the CSV files to save all data, enable averaging for the calibration, enable user calibration kits, and finally allow output powers from -20 to 0 dBm, if that's possible. This I'm not sure about because I'm not completely, I don't know the configuration of the hardware inside, but if they can do this, this should be done. These changes would turn this from a barely usable, the VNA option from barely usable, into a highly useful tool. Anyway, some other nice to have features would be sweep spans less than 5 megahertz, which would be useful for aligning IF stages. or perhaps for, you know, some ham bands if I just want to sweep over the band. Simultaneous display of magnitude and phase. You know, I could display the phase, and then I have to go to the then I have to go to a different screen to magnitude for magnitude. You know, you have different colors. You could display them both on the same screen. That would be really nice. Now these last ones are kind of because I'm more an analog guy at heart than RF. I'd like to be able to, like, instead of looking at a Smith chart, look at the log of impedance and the phase of impedance versus the log of frequency, and look at the log of, let's say, for S22, not S21, not S22 as it says here. Look at the log of S21, the phase of S21 versus the log of frequency. It would be and, you know, for log sweeps, it might be possible to get away with a lot less than 761 points and still have it look good. Anyway, the conclusion is this is a very nice spectrum analyzer for the price, especially because it includes the tracking generator. The network analyzer is an interesting but flawed option, but with some firmware changes, it could be great. I hope Siglent sees this and takes some of my suggestions. Anyway, if you like this video, please give it a thumbs up. And if you'd like to see more videos from me, please consider subscribing. Thank you.